communication technique is using barriers. So far, what we did was we always use producer-consumer problem example. With the producer-consumer example, there is one or more than one producer and one or more than one consumers. One is producing, the other one is consuming. In this case, we need to synchronize between the consumers and the producers. Sometimes the inter-process communication mechanism uses some other scenario, like it's not somebody is producing, somebody else is consuming. It is it's something like this. These four processes or threads, they can continue running in parallel, okay, without any communication between them. But when they reach this point, they all have to wait. They all have to wait until all of them are here, okay? All of them are here. When all of them are at the same position, then they can continue. This is called barrier, okay? Sometimes we may need inter-process communication under these circumstances. It's not like producing or consuming. It is if everybody is at the same if everybody is at the same phase, then all of them can continue working on some other problem. Okay, so they are waiting for something to happen. This is called barrier. It's a way of inter-process communication. I will not look at the detail of these barriers, but you should know that there are things like those. Let's say this is usually done when this is usually, you know, the classic example is this. You know the videos, right? What is a video? Video is a one frame another, one picture another picture, right? This is picture number one, this is picture number two, and this is picture number three, and this is picture number, let's say, 4. So I have how many pictures in a single second? I have 25 pictures in a single second, right? And each picture is 4,000 lines and 6,000 columns, right? So there are 24 million pixels available in a picture. There are so many of them. So if I wanted to process this picture using multiple threads, I might say that, okay, I might say that, divide this picture into 4. This will be thread number 1, thread number 2, thread number 3, and thread number 4. So my 4 threads are processing this picture in parallel. So they are not dependent on each other. They can continue working on it, okay? But before starting working on this picture number 2, all of these 3 threads should be done so that I can load a new picture and start working on this new picture. So I put a barrier here, okay? I put a barrier. I would say that all of these 3 threads have to complete their jobs before they can go on working on picture number 2 and do the same thing with the picture number 3. Okay, I cannot do this. I cannot have T1 working on this part and T2 is working on this part, because I need to load this picture number 2. Okay, I need to load this picture number 2, and I need to erase this picture number 1 from my memory because it is taking so much memory. Okay, so in this case, instead of doing something like a producer-consumer model, it doesn't work in my case. There is no producer, there is no consumers. Everybody is producing, everybody is processing pixels, picture elements. In this case, I would use barriers. So this is one example of inter-process communication again. I will skip this part, avoiding logs, because I am so behind the schedule. So you can read it, but I will not ask any questions about read, copy, update features. Okay, I'm going to start now on a new topic. This chapter had 3 parts. We talked about processes and difference between threads, general concepts. Then we talked about inter-process communication. Now we will talk about scheduling. How do I schedule more than one process or thread on a single or multiple CPU? Okay. So if I have two threads or processes, doesn't matter. And this is how they work. The first thread is using lots of CPU time. Then it will block because it is waiting for some I/O operation. It is waiting for some I/O operation here. So it will be blocked for this duration. Then it will continue running using the CPU, and it will be blocked and running. So this thread A or process A is using lots of CPU time. Okay, so it's a CPU bound process. Thread A or process A is a CPU bound process. For the process B, it uses a small amount of CPU time, and then it will block because it is waiting for an I/O task. Then it will run again, and then it will block. Okay. So these are two different processes, and I need to schedule them. If they are running on my CPU, single CPU, I need to schedule them so that my CPU usage is more efficient, my system is more responsive, my overall efficiency, system efficiency is high, etc. Those kind of concerns I have. Okay. So this part of the chapter looks at this problem: how do I schedule these two or more than two processes on the same CPU or on multiple CPUs or on the same system? So this is called scheduling. Okay. These are the questions. I have several processes runnable. They are available to run. So which one should I pick next so that it will run? Okay. So many different ways to make this decision. And to make this decision, we need to set up many different criteria. I would say that if efficiency is my concern, then I would make a different decision. If interactiveness is my concern, then I would choose something else. So many different ways to make this decision in the scheduling. Scheduling is a very complicated, very detailed task actually. Okay. So when we start from the beginning, from the 1950s, the batch systems, remember what's the batch system? Batch system does the same thing over and over again. It doesn't. For example, bank transaction processing. In a bank, you have maybe 10 million transactions in a single day. So somebody has to process all these transactions. Or at the end of the month, you need to calculate the payrolls of all of your employees. Let's say if you are the government, Turkish government, then you need to pay their salaries at the end of the month. That means that you need to make calculations for 2 million people. Sometimes each calculation may take some time because it is complicated. These are batch systems. In the batch systems, scheduling did not matter much because you have all of your data to yourself and the same task runs for 6 hours. So you don't have more than one task that needs to be run in parallel. You complete one task and you start another task. So there is no scheduling actually. In fact, there is a scheduler, that scheduler is the person. That person who lost the cards or the tapes on the computer, then the task of the schedule is done by that person in the 1950s and 60s. And nowadays it is actually the same for the batch processing system. You don't do much scheduling. There is only one decision to make: which batch task should I do first? Okay, there is no switching between the batch tasks. You have to you start with one batch task and you complete it, then you switch to others. Okay. So for the batch systems, that's the picture. For the other type of systems, like the hybrid batch or time sharing systems, they give priority to short time sharing requests. Okay. So the picture is different now. for the time sharing systems, priority is to the short time sharing request, so that I can stay interactive, okay? So that I can stay interactive. That's a common policy most of the people use, okay? Must give priority to interactive requests, okay? So if I have two processes on my computer, one is taking the system backup, which might take a few hours. The other one is the interaction with the user on a word processor. Which one has the more priority? Of course, the interactive request has the more priority, because I expect, as a user, I expect my system to stay interactive, whatever the system is using. I don't expect my backup process to be interactive, because it doesn't need any interaction. So the priority is to the interactive request. Most of the time we will say that our policy is to give priority to the interactive requests. Okay, we already know this. Processes alternate CPU use with I/O requests. When I have a process, I am using the CPU. When I do the I/O, most of the time I will get blocked, and another CPU will take another process will take the CPU, and it will continue using that CPU until that one blocks. I/O requests frequently block, either waiting for input or when too much has been written and no buffer space is available. Okay, so it is waiting for somebody else to use that space, use that data, so that space is available. Okay. CPU-bound processes think more than they read or write. So this is a CPU-bound process. This is a I/O-bound process. Those CPU-bound processes, they use more CPU. By think, it means CPU using more CPU time. And I/O-bound processes do lots of I/Os. Okay. When they do lots of I/Os, I mean it is not that the I/O operations are so time consuming. The I/O operations are when the process says that I need this I/O, that's it. The process goes to sleep. It doesn't take the process's time, but the overall time for that process is long, because the I/O operation to complete will take some time. Okay, so the absolute CPU speed of CPU and I/O devices is irrelevant. We don't care about when we are doing the scheduling. Actually, when we are doing the scheduling, we don't care about the CPU speed or the I/O speed. What matters is the ratio of the speed differences. Okay, CPU is much faster than the I/O devices. We know that. The ratio of the speed difference, what matters when you are doing the scheduling. Okay, it is not the absolute speed of the CPU or I/O devices. And most of the time, this is the main rule. CPUs have been getting much faster relative to the desks. So when the CPUs are getting much faster relative to the desks, okay. So this picture and this picture, so this I/O wait areas are getting longer and longer with respect to CPU usage. Okay. So that means that most of the time CPU will be used in a very short amount of time, and most of the tasks will be waiting for the I/O task to happen. Okay, so this will be one of the main concerns of scheduling for the modern operating systems, because the ratio of speed differences between the CPUs and I/O devices. Okay, so these are the moments. These are the time positions where we need to make a decision on what to run next. Okay, a few of them, actually, almost all of them are here. After we created a new process, after a fork, okay, we need to make a decision. When you make a fork, you have now two processes. One is a parent process, the other one is a child process. You need to make a decision which one to run first, for a child or the parent. If you have a single CPU, you cannot run both of them at the same time. So you need to make a decision. So this is a scheduling decision, okay? If one process exits, if one process says that I am done, exit 0, then I should make a decision what to run next, which process to run next, another scheduling decision. Another one is when the process blocks. What do I mean by blocks? When the process asks for an I/O, the process says that I want to write to the disk, or I want to read from the keyboard, or I want to write to the screen, or I want to send a package to the network, that kind of stuff. When the process blocks, then I need to make a decision. Which process to continue. And when I/O completes, this is again another position where I need to make a scheduling decision. When the I/O is complete, what happens when the I/O is complete? Can tell me the number of steps, the steps that the computer takes when the I/O is complete. When the I/O is complete, what happens? When do I get blocked? When I say this, when a process blocks. When does this occur? When a process blocks. Upon what condition my process blocks? If I make an operating system call, okay, and if that call cannot be done at that time, so my process blocks. I know that, right? So to make my process block, I need to make an operating system call. How about this one? When do I know that the I/O operation is complete? Who does the I/O? CPU doesn't do the I/O, right? My process doesn't do I/O either. Who does the I/O?
Operating system.
No, not operating system. Yes, control. That's a device, special device that controls the I/O device, right? I/O control does the I/O. When the I/O is complete, what happens? Yes, the I/O device creates an interrupt. It tells the CPU that the I/O is complete. Okay, and whatever the interrupt number is, that interrupt handling procedure is found, and it starts executing. So when the I/O is complete, an interrupt occurs, and the operating system takes the control and needs to make a decision. Should I continue running the same process, or should I let the process that initiated this I/O continue? Okay, that's another scheduling decision. Okay, and sometimes after the timer interrupts. What do I mean by timer interrupt? For most of the computers there is a timer, and timer interrupts happen every 50 times, 60 times a second, depending on the system. Okay. After the timer interrupt, the operating system again it's like an I/O interrupt. It's a timer. Timers are I/O devices actually. Okay. Timers are. Your disk is an I/O device. Okay. Your screen is an I/O device. Your printer is an I/O device. Timers are like I/O devices. They are not part of the CPU. They are not part of the memory. Okay, they are your devices. Okay, you communicate with your device. You ask your device to produce a timer after 60 milliseconds, and it produces an interrupt, like the I/O device. I/O controller produces an interrupt when the data is ready. This one produces an interrupt when the time is up. So after the timer interrupt, like this one, I might have to switch from one process to another process. So these are the positions where I need to make some scheduling decisions. And depending on the system, depending on your priority, you should choose one. Well, when I talk about each of them, I didn't give an answer, right? I didn't say that after a fork you should always run your parent process. I didn't say that. Or I didn't say after a fork you should always run your child process, right? So there is no single answer, there is no correct answer to each of them. On the process exit or on the process block, there is no single correct answer for each of those. It depends on your motivation, it depends on your system. If you have a real-time system, okay, your decisions will be different. If you have an interactive system, your decisions will be different. And if you have a batch system, your decisions will all be different. Okay? So when you make those decisions will be dependent on the environment that you are working on. Okay, let's look at a few scheduler types. Preemptive and non-preemptive schedulers. Okay. Actually, we talked about this some time ago, but you might remember this. In a non-preemptive scheduler, it will let the process run as long as it runs. Okay. You let your process run as long as it runs, but it will not run. Infinitely long unless it is calculating all the digits of the number pi or number e, the scientific computation. Sometimes, okay, after it will run for a while, there will be a time where it needs to make some I/O, okay, where it needs to talk to the operating system, okay. In that case, it will block, okay. When it blocks, the scheduler might let another process use the CPU. Okay, in the non-preemptive scheduler, it is up to the process to release the CPU by saying to the operating system that I need this data, or I need to, I am done, I am not going to continue. This is non-preemptive scheduler. In the preemptive scheduler, the opposite way, it uses some time quantum. What's a time quantum? Time quantum is a time duration. It's a time duration, let's say 10 milliseconds. After 10 milliseconds, the preemptive system stops the process and lets some other process take the CPU. This is called preemption. Okay. So most of the modern operating systems are preemptive systems. They use this time quantums, and the duration of the time quantum is something adjustable, something critical for the system performance. Okay. So, but to do this time quantum, you need a clock interrupt. So you need as I said before, this one, time interrupt. You need a special device, a clock, okay? The clock has to produce an interrupt at the end of the time interval to give the control of the CPU back to the scheduler. So without having a system clock, interrupt clock, writing a preemptive system is not possible. Okay, if no clock is available, non-preemptive scheduling is the only option. And clock may not be available for some systems. So preemptive is more flexible in terms of running many processes at the same time. Okay, any questions so far? So we are done with inter-process communication. We are talking about which process should run next question. We are trying to answer that one. Okay. These are again, if I wanted to classify the schedulers in terms of preemption and non-preemption, there are two categories. Okay. If I wanted to categorize them with a different criteria, I have these three new categories: batch systems, interactive systems, and real-time systems. Let's look at these systems in terms of preemptiveness or non-preemptiveness. In the batch system, responsiveness isn't important because the batch task, you don't need any interaction, so it doesn't have to be preemptive. So preemption is moderately important. It is not that important in the batch system. It could be non-preemptive system. But when it is interactive, okay, it must satisfy a human, and preemption is important in the interactive system. You cannot have a process taking the CPU for 20 minutes in an interactive system. For the real-time systems, it is often non-preemptive. Tell me an real-time system. What kind of system do you have in mind when I say interactive system?
Nuclear plants or something.
Yeah, the main computer of the main operating system of the nuclear plant, controlling plant, is real-time system. But maybe you can give more real life, everyday life example.
Arabalardaki sistemler.
Fabrikalardaki algısı.
Entertainment systems, right? Entertainment systems. What do I mean by, for example, this one? This is a phone, right? So when the call comes, this one has to respond in a fixed amount of milliseconds. Otherwise, the call will not be answered. Okay? Or when I try to make a call, it has to give me a response in a fixed amount of time. That's what means that. What is the definition of real time? Real time means that whenever it takes a task, that task has to be complete in, let's say, 10 milliseconds or 100 milliseconds. There is an upper bound. You cannot be late. Okay? In the real time tasks, you have to be always on time. Otherwise, nuclear power plant will explode. Otherwise, you will miss your calls in the cell phone. Otherwise, your car brakes will not work, right? So, in the real-time operating systems, time is so important. But it says that they are non-preemptive. So, interaction is very important in the entertainment system case or the cell phone case. Interaction is very important, but it says that real-time systems are often non-preemptive. How can this happen? It is counterintuitive, right? It says that it has to be every task has to be completed in a certain amount of time, but it's non-preemptive. So how do you explain this? İlk ders gelmeyenler niye gelmediler? Ha? Ders gelmeyenler şöyle işaretlesin. Başka kimler var? Anladınız mı soruyu? Ne soru? Soruyu söyleyin bari.
Neden real time'de non gelmiş?
Real time olduğuna göre preemptive olması lazım. Preemptive neydi? Çok fazla kullandım. Ben seni kesiyorum, başkası kullansın da, değil mi? Real time'lar öyle değil diyor. Real time'lar non-preemptive. Yani zaman kısıtlı diye bir şey yok. CPU'yu al, istediğin kadar kullan. Öyle bir şey olamaz ki ama. Bu yanlış değil, doğru yazmış adam buraya. Okuyun kitabı, kitapta da aynısı yazıyor. Niye böyle?
O süreye kadar yapım, yani mesela o sürenin yarısında kesilse de aynı sonuç verecek. O sürenin sonunda olsa da aynı sonuç verecek.
Neden?
İnsan etkileşimi mi gerekiyor? Maksimum süre mi?
Hocam çalışacağı zamanlar belli değil mi real time'da? Şunu yapacak, sonra diğeri çalışacak. Zaten belli bir kısıtı var yani ayrılmış.
Zaten real time olduğu için sistem, tamam, sistem zaten real time olduğu için hiçbir proses alıp CPU'yu 10 dakika kullanacak şekilde yapılmıyor real time sistemler. Öyle bir proses yok. Eğer öyle bir şey olsa zaten real time olmazdı. Real time ne demek? Herhangi bir verilen görev, işletim sistemi görevi ya da diğer görevi işini 10 milisaniye içerisinde, 20 milisaniye içerisinde yapmak zorunda zaten. Değil mi? Eğer bir task işini alıp bir dakika sürerek yapacaksa o zaman real time'dan çıkıyor. Öyle bir real time sistem olamaz. Zaten real time sistemlerin çoğunun diski falan yok, biliyorsunuz değil mi? Adamlar da I.O. yapmıyorlar. Niye I.O. yapmıyorlar? Çünkü I.O. yaptığı zaman disk gibi bir yerlere falan filan o alıyor 300 milisaniye. O zaman real time'de bozuluyor. Real time sistemde hemen böyle işte mekanik bir cihaz üzerinde I.O. yapmak gibi bir şey yok. Network bağlantısı da yok real time sistemlerde. Real time olan tarafı. Bazen sistemin hem real time tarafı, real time olmayan tarafı var da öyle bir şey yok. Yani bir arabanın fren mekanizmasını, motor ateşlemelerini falan kontrol eden bir real time sistemi düşünürseniz Yani frene basılmış, onun iletilmesi lazım, tekerlere falan gitmesi lazım. Arada bir de 100 milisaniye şurada bir disk backup alayım falan filan gibi bir şey yapamazsınız, olmaz. Yani arabanın 15 yıllık ömrü boyunca bir defa hata yaptığı zaman o kodu yazan firmanın birdenbire 20 milyar dolarını altını çöpe atın. Aynen böyle oluyor. Ne oldu? Freni tutmadı. Bir iki defa olmuştu şeylerde. Toyota'larda olmuştu herhalde. Frenleri tutmuyor muydu? Gerçi bilgisayar hatası değildi falan ama yani yapamazsınız o tür şeyde. Dolayısıyla real time olduğuna göre belli bir süreçlerden geri gelmesi lazım. Hiçbir proses belli bir kuantumdan, tamam mı? Şurada diyorduk ya, hem kuantumdan daha fazla zaman zaten almayacak tasarımları gereği o. O nedenle that's why real time systems are often non-preemptive. They don't need to be preemptive.
Hocam bir şey sorabilir miyim? Robotlarda hani belli bir iş yapıyorlar ya, mesela real time sistemlerde şu belli, şunu yapacak falan ama mesela makinelerde machine learning'le beraber şey çıkıyor ya, yapay zeka. O sanki real time'ın içinde de bir preemptive bir dallanma olmuş gibi olmuyor mu? Hani küçük bir şey var mesela, düşünce yapısı var. Biraz daha zaman isteyebilir belki CPU'dan. Hani illaki non-preemptive olacak diye bir şey yok. Tabii şey olarak, yani machine learning'le.
Eğer real time system'sa, tamam mı?
Yine real time gibi ama hocam.
Real time system'sa ve real time sistemin her bir task'ı belli bir kuantumun altında kalmıyorsa real time sistem diyemiyor, garanti vereceksin. Sen diyorsun ki bazı algoritmalar daha fazla zaman alabilir falan pişman. Şimdi şeyi karıştırmayalım. Adamın yapması gerekli bir tane ana görev var. Tamam mı? Ne mesela? Robot buradan çıkacak, gidecek, bir şey toplayacak, geri gelecek. Yapacağı iş zor. Yapay zeka gerektiriyor. Ama onun için real time olmasına gerek yok onu yapacak sistemin. Real time olması gereken sistem ne? Robotun saniyede şeylerinden, özellikle hikayenin üzerine doğan bir robotsa falan, sensörlerinden saniyede 50 defa şey okuyup, veri okuyup, 50 defa motorlarına actuation yapması lazım. Diğer türlü robot ayakta duramıyor. Real time olacak tarafı bu. Sistemleri birbirine ayırt edebilirsin. Üst tarafta akıllı bir sistem var, o real time çalışmıyor tabii ki. O bazen dakikalar alıyor bir şeye karar vermesi. Ama alt tarafı çalışan real time sistem görevi basit bir sistem o. Robotun sürekli olarak ayakta kalmasında hiçbir zaman dengesinin bozulmamasını sağlar. Ona benziyor yani. Okay. So when we do the scheduling decisions, okay, when I say that I don't have any single answer to all of those questions, I need to set some goals for my scheduler, okay? So these are some common goals. Fairness is one of the most common goals of the all schedulers. Each process should get fair amount of CPU time, okay? Fair amount of CPU time. That doesn't mean that each process will get the equal amount of CPU time, because if I do that, then I wouldn't have any priorities. So fairness is something common to all systems. I should say that my system should be fair with respect to assigning CPU times for each process. That's one common goal. Another common goal is policy and enforcement. Each scheduler has its own policy. Okay. What do I mean by policy? Depending on your system, for example, for the real-time systems, my policy is, it is always, each task should be complete in a given amount of time. No process can take more than 100 milliseconds to complete this time. This is my main policy. So the scheduler should enforce this policy. I cannot escape from this goal. And the balance, again, it's a nice thing. I should keep all parts of the system busy. Okay? If my bottleneck is the disk, I should keep my disk busy so that my processes are not waiting for it, or my I/O devices. My scheduler should make a decision so that all of my parts are not sitting idle. At least some of them are always busy. So these are my scheduling. General scheduling goals. Other than this general scheduling goals, I have specific goals depending on the system time. For example, for the batch systems, I should maximize these. I should maximize throughput. Throughput means maximize jobs per hour. how many jobs did I complete in a given hour? Okay, how many jobs did I complete? That's the main goals of a batch system, so that I can complete more jobs. Okay, by throughput. Turnaround time is another goal for the batch systems. Jobs should return quickly. Often we want to finish short jobs very quickly so that they don't have to wait for the long jobs to complete. And CPU utilization is another goal for the batch system. CPU utilization is not a common goal. For some systems, I don't care about the CPU utilization. Why? Give me an example of this. CPU utilization is not important for the system. What kind of system is that? I mean, you always want, for the batch systems, you always want your CPU to be utilized 100%. You don't want your CPU to sit idle. But for some systems, you don't care about the CPU utilization. Yes?
CPU kiralıyoruz ya hocam bazen şeylerde, ağzında falan. O zamanlarda CPU utilization full yapmazsak, %100 kullanmazsak sürekli para harcıyoruz. Boşuna olmaz.
İyi de o zaman kullanman lazım. CPU utilization'ın önemli olmadığı bir şey. Sen tam tersini söylüyorsun. CPU utilization'ın önemli olduğu bir şey söyledi sen.
Evet.
Ben önemsiz olduğunu soruyorum. CPU utilization yok, önemli değil.
Bilgisayarlarımızda öyle mesela.
Evet, bizim kullandığımız PC'lerde hemen hemen öyle değil mi? Ben şimdi şu bilgisayar çoğu zaman sizce ne kadar mı kullanmışımdır ben bu CPU'yu? Binde birini kullandıysam şanslıyım, yok pardon. CPU hemen hemen bir şey yaptırmıyor ki. Arada bir sadece şöyle yapıyorum, bir de arada bir şey geliyor. E-mail falan geliyor, burada bir şeyler çıkıyor. Yani %1'ini kullandığını hiç sanmıyorum bile. Umurumda mı peki? Çok da değil. Niye? Benim amacım bu CPU'yu alıp bu CPU'yu olabildiği kadar verimli kullanıp buraya yatırdığım parayı 17 içerisine çıkarmak falan filan değil. Ders anlatmak değil mi benim buraya? Yani ders anlatırken interaktif kalsın. Benim için CPU utilization daha çok interaktivitesi bunun. Buraya şuraya bastığım zaman bunu yapabilmesi beklediğim tek şey burada. Burası CPU utilization. Hani bazıları scheduler önemli CPU'yu olabildiği kadar çok kullanmak falan hayır değil. Batch sistemlerde önemli ama batch sistemlerde, çünkü batch sistemler büyük pahalı sistemler. CPU'yu ne kadar tutarsan, biz tutarsan o kadar sistemini iyi kullanıyorsun demektir. Şey gibi, yani şehirler arası otobüs sahibi olmakla normal işte binek araba sahibi olmak gibi. Şehirler arası otobüs sahibi olanlar arabalarının sürekli çalışmalarını isterler. Niye? Adam oraya 1 milyon lira vermiş. Kaç lira otobüsler?
70.
1 milyon mu?
700
Ha,
bin
şey.
falan.
700, tamam 1 milyon. 1 milyon yatırmış oraya, 1 milyonunu 5 yıl içerisinde çıkarması lazım. Çünkü onların ömürleri 5 yıl mı? Kaç yıl otobüslerin ömürleri? 5 yıl içerisinde çıkarması lazım, üzerine para kazanması lazım. O otobüs gece yerinde yatamaz. Otobüsün sürekli çalışması lazım. Ama binek arabalarda öyle değil mi? Binek arabada benim derdim, ben bu arabanın parasını 5 lira çıkarmak için falan filan diye kullanmaya çalışmıyorum. Binek arabadaki şeyimiz beni bir yere götürsün, getirsin falan filan. Ya lazım olduğu zaman çalışsın, yolda kalmasın. Çok da fazla yakıt harcamasın falan gibi önceliklerimiz var. Operating sistemde de yine aynı şekilde. Yani her zaman için resource'un dolu olması benim önceliğim olmayabilir. Şuna da yine aynısı. Yani CPU %100 çalışsın dediğim zaman esasında CPU'nun çok fazla çalışmasını istemiyorum ben burada. Şu 4 tane makinede bile CPU %100 çalıştırırsam 10 dakika sürer mi acaba şunun pilinin gitmesi? En kral telefonu yani 1 saat içerisinde çok rahat bir şekilde pilini yersiniz, bitirirsiniz CPU %100 çalıştırırsanız. Başka burada throughput var. Throughput ne demek? Saatte yapılan, bir saatte kaç tane iş bitirir ona bakıyor, önemli. Benim PC'm açısından hiçbir önemi yok onun, cep telefonu açısından hiçbir önemi yok. Bir de turnaround time. Turnaround time ne? Verilen bir iş ne kadar zamanda yapıldı? Şununla şu birbirinden çok farklı değil mi? Birisi verilen bir iş ne kadar zamanda yapıldı, bitti, yapıyor. Birisi saatte kaç iş yapıyorsun'a bakıyor. Yani şunu saatte kaç iş yapıyorsun'u bazı işleri çok geciktirerek hızlandırabilirsiniz. Anladınız mı? Mesela bir tane şey var, uzun bir proses var, 1 saat alacak. Bunu beklet diyorsun. Niye öbürleri 5'er dakika alıyor? Ben 5'er dakikalık şeylerden, proseslerden 20 tane yapsam, tamam mı? Throughput'un ne oluyor? Saatte 16'ya falan çıkıyor değil mi? 5'er dakikalık yaptığımda. O adamı bekletiyorum ben. Niye bekletiyorum? O çünkü aldığım zaman 2 saat alacak. Birdenbire throughput'um 2 saat çalışırsa saatte yarıma düşecek. Tamam. Ama turnaround time bu sefer artmaya başlıyor onun için. Niye? O adam akşama kadar beklemek zorunda. Öyle bir iş için turnaround time'ı benim bayağı bir artıyor. Yani bunlar birbirleriyle çelişen şeyler, throughput ve turnaround time. So they are sometimes in conflict. You cannot satisfy both throughput and turnaround time at the same time. You need to make a trade-off decision between those. So these are the goals for, these are general goals. Okay, these are goals for the batch systems. Okay, for the interactive systems, my main goal is the response time. That's it. Okay, I don't care about the CPU utilization. I don't care about throughput. I don't care about turnaround time. Only the response time. Respond quickly to user requests. Okay. By the way, when I say quickly, there is human psychology involved in here. Okay. Meet user expectations. The users does not want everything. Of course, they want everything to be fast, but sometimes they say that okay, this may not be that fast. For example, when I say that take my system backup. When I take my system backup, I know that it's going to take at least a few hours, or update my system from Microsoft. Okay, how many minutes does it take? Sometimes it takes an hour, 2 hours, 3 hours, right? So the user doesn't expect the system to be updated in half a second. That's the user expectation. But sometimes when I do this, okay, I expect this screen swap in half a second or 1/10 of a second. This is my expectation. Okay. When I move my mouse, I should see my mouse moving, right? If it takes half a second longer than what I expect, then I would say that this is not the interactive system. So this is my expectation, and it has something to do with the psychology, human psychology. Users have a sense of cheap and expensive requests. For example, this one, when I do this, this is a cheap request. That's why I expect that it will be done in a quickly. Sometimes there are expensive requests, like the system update. Those are, in my mind, I say that this is cheap, although it's not cheap. Lots of things are going on, and taking the system backup is expensive. Okay, users are happier if cheap requests are finished quickly. When I do that cheap request, like the mouse movement, or entering my name, or reloading a page, these are cheap requests for me, and I expect that cheap requests finish quickly, and expensive requests might take some time. It might take some time. The cheap and expensive are user terms. They are not terms for the operating systems, and sometimes cheap and expensive don't always correspond to reality. Okay? When I say cheap, that cheap thing might be very expensive in terms of CPU utilization, system resources. And when I say expensive as a user, that expensive thing may not be that expensive thing. May not be that expensive. For example, system update. It takes so long time because the Microsoft servers are so slow. My network connection is okay. I am not using my CPU time at all. I am not using my CPU connection fully, internet connection fully. Still, I have to wait for a long time. It is not because it is that expensive in terms of CPU utilization. It takes long time because the connections are slow. Okay, so this human psychological behavior gives us these two things: cheap and expensive requests. Okay, let's look at, okay, these are interactive systems. How about the real-time systems? Goals of the real-time systems. Meet deadlines. That's the main goal. In this case, it was the response time. In this case, this was throughput and turnaround time. But for the real-time systems, it is meeting the deadlines. When I receive a task, I should be done in 10 milliseconds. Otherwise, my video player will skip frames. People will not like it. More seriously, my brake will not work on my car, and I might cause some accident. And it will be predictable, okay? Users must know when the request will finish. Okay, it is predictable. Okay, when I hit a button, I know that in a certain amount of time I will get my response. Okay, and it requires very careful engineering to match priorities to actual completion times and available resources. If you don't have a real-time system, you have to be careful, but you don't have to be real careful about this one. But in the real-time systems, you need to know what your I/O devices can do, what kind of capabilities they have, and what kind of things you can ask them to do in a certain amount of time. Very careful engineering to match priorities and actual completion times. So these are the real-time system goals. As you see, depending on your system type, your goals are changing. Okay, so I think I am out of time. If you have any questions, I will answer the questions, but I will stop here. Any questions? I need at least one or two questions before I will let you go.
In interactive systems, we want the system to react in real quick time.
Not in real time, but in a quick amount.
Interactive. Isn't that indirectly about turnaround time? Isn't that important?
When in the turnaround, in the batch systems, turnaround time is a term used for completion time of the processes. Okay, a process starts and process ends. Okay, in interactive systems, usually when I do an interaction, my process still continues but stays interactive. Okay, so you might say that they are the same thing, but the definition of turnaround time is it is done. How many jobs did you complete in a given hour? How many processes did you complete? For the interactive case, my process still continues, okay, but it stays interactive. You might see it that way, but the standard definition is done this way. Okay, başka soru var mı? Soru. Tamam, artık öyleyse yarın sabah burada